I'd like to introduce my co-chair, Faith Vilas, who will be talking about ultraviolet observations of primitive asteroids.
Okay, welcome to the last talk of the contributed talks at the meeting. And thank you for sticking it out. I hope it's not dreadfully boring in any way, shape, or form. You never know. So what we have started to do is to take a look at the ultraviolet spectral region and take a look at asteroids. We've looked at the S-complex asteroids. This is me and Amanda Hendricks, whom I will point out that we are both members of the Survey-Trex team, and I'm also a member of the Survey-Class team. So anyway, we started looking at the UV blue spectral region, looking for different spectral features, and we started this by taking a look at old IUE data. In this case, we're talking about the C-complex, or the primitive or dark and presumed primitive asteroids that we have. We looked at the C-complex asteroids that were taken by the IUE back in the 1990s. These are older data. They have less spectral resolution, slightly noisier, but I think they're still usable for this, and I'll show you why. We then followed it by, I got six spectra of 6 asteroids with the MMT because it has a pretty good response in the UV. And we also incorporate in this 8-color, 24-color photometry, SMAS spectra, Vilas spectra, and Sawyer spectra from the small bodies node. So you'll see a lot of other data. That's what they all are. Very quickly, this is Ceres, and it was actually taken with HST only a few years ago. I'm showing you this because it goes into the UV, and what I want to do is to demonstrate that let's see, well, no, I can't figure it out. I deserve this. Okay, there. No, don't worry. That much I do know. The spectral region is roughly the same here from this darkened area, and the agreement in the general shape and characteristics of the IUE data, which are down here, coupled with some other ground-based data that we have of these asteroids, or of Ceres, and the HST data are roughly the same, and we use that, even though there is additional scatter here, we use as an indication to us that we can take the IUE data with validity. So the first question we asked was, are there UV blue spectral attributes that suggest compositional information in these data? And I find the right one here. So again, here I'm going to show you some spectra of laboratory spectra of different variations of carbons and carbon compounds. They're reflectants, absolute reflectants. They vary here. They're from Papular. Hendricks et al. Presented them. And I'm showing you the cutoff here at about where we normally would cut off our ground-based observations. If you go beyond that and take a look, you see there's quite a bit of structure out here, and it does vary depending upon the composition. These are ordered in increasing level of graphitization, which means removal of hydrogen for practical purposes here. So we think that this might be a rich region for some information that we do not get in the spectral regions that we normally observe. So very quickly also, this is the more detailed description. These are from Buss and Binzel, and roughly B classes, Cs, CGs, C, GH, and CH, which have the 0.7 micron feature in them. And you see the drop-off, that's usually the UV blue IVCT, and all the C classes. The Bs are not. They are pretty flat. They do tend to curve down blue, as we saw earlier today. And so if we went into the UV, what do we see, and what changes might we find out? So we'll look at all of the ones that are divided by spectral type. Starting with the B class, this is what we'd see if we're looking only 0.44 microns and higher. Here, this line delineates where we cut off for the visible data in most of the examples we were showing. And here in the blue, you see that there's quite a variety in the B class. A couple of things to note here. One is there is a turnover in the B class. It just happens to be at a lower wavelength region that we've looked at. And we see quite a variety in the spread of information in the spectra in the B class, including an absorption feature located right about here. Down here, this is the standard definition of what a B-type is. Okay, C. C class, same thing. They're all very uniform, and they are pretty uniform. We only have two up here right at the moment. They're pretty uniform in the visible. They're pretty uniform in the blue. And they don't show any of the extra features, I don't think, that we saw in the B yet. CGH, which is the stronger version of the asteroids that have a 0.7 micron feature. You see that, and you also see some variation in the blue, and it still remains a strong drop-off into the UV. And the CHs, again, same sort of thing. They're pretty uniform, and they're pretty close to the same. So we have some variations here, and a lot of this is occurring shortward of 0.55 microns or 550 nanometers. You see this interchangeably. So we wondered if we could learn anything about the differences in this from our spectra, what causes the pronounced UV absorption that's stronger in the C, G, and CGH as opposed to the C and CH types, whether it does or doesn't have a 0.7 micron feature. And what do the B types have less of a UV absorption than the C complex? Well, actually, the B types do have the UV absorption. It's just at the shorter wavelengths, like I said. And for most materials, we are going in with the assumption that the main cause of the UV absorption is the UV blue IVCT caused by iron oxides. Great, I'm going to have to rush this one. See, I pay for it, it comes around. So we felt that we had a couple of hypotheses. Among the low albedo class asteroids, we thought the shape is affected by the presence of opaque weathering products, which include carbons potentially. So we did some quick spectral models of intimate mixture models of phyllosilicates, serpentines based on laboratory studies of CM2 carbonaceous chondrites and amorphous carbons. And we started out by doing it, seeing if we could match roughly what we were seeing, and using a lot of percentage of carbon. The variation in like the 70% carbon will have a variation in particle size ranging from 10 microns to 30 or 40 microns in diameter. And we ended up with way too much carbon, period. And that's it in absolute reflectance. So we went back and we varied a mixture of really small to really large particle sizes, and the intimate mixture of the varying sizes got us down into our absolute reflectance values that were not dissimilar to what we have been seeing. So particle size plays an issue in this, which is what I think people who have been pointing out or predicting IDPs on solid surfaces as being what might be present also are running into. The question of what is the size? Occam's razor to me says maybe it's a mix. So let's see. Also, then, can it be used to discern space weathering effects on a C-complex asteroid surface? And I'll see how fast I can make this. The UV absorption seems to be present at less than 400 nanometers. We think it's actually decoupled from the 0.7 micron feature, which we find it's normally coupled with the 3 micron water of hydration. And so we went to take a look at weathering effects to see if carbon combined with, say, nanophase iron is what is causing us to have the darker features. This we did for the C-complex asteroids. Take a look at Hapke's model. I'm going to go through this fast. And we remodeled it and determined that through a previous study that we will see the onset of UV blue effects in a spectrum with a much smaller percentage of nanophase iron than you will before you start seeing the onset of this in the V and IR, which means that the UV blue for the C-complex asteroids is more sensitive. What? Thank you, S-complex. I was more sensitive to the added NPFEO, more so at the UV blue spectrum than at the longer wavelengths. So we went to see if this is not the same for the C-complex, and this is where we're still in work in progress. We have an indication that there's about maybe 12 to 20% of olivines that are present in the CM2 carbonaceous chondrites. Those seem to be the best analogs so far for what we're studying. It's a small amount, but you only need a very small amount. The olivines are present in the chondrules. They're not present in the matrix. Carbon would be present in the matrix. We've seen spectra of the matrix material, but spectra of the chondrules has not. I'm not aware of any spectra of the chondrules. So we wondered if we see this effect in UV in the C-complex asteroids that we also saw in the S-complex. And how does this affect the UV blue absorption edge? We actually limit this and think that maybe a combination of olivine and carbon because because of the presence of the carbon features or probable carbon features and the fact that at some point we don't see the reddening, this significant reddening that you see in the S-complex asteroids. So we went to take a look at our CCD spectra, and the one that was most interested is the CGH 3507 Vilas. I can't help it, it was a target of opportunity. And it does seem to show, as some of the others do, the same kink that we think is the transition between the volume to surface scattering that we saw. These are all that have the 0.7 micron feature in them, so we know that we expect them to have some irons for sure. And we are seeing the same sorts of things and the possible same sort of overturn or kink that was the indication for us of the weathering process occurring. Anyway, at the end, where we are, and we're still working on this, we extended this coverage of low albedo asteroids for the primitive or very, very dark albedo asteroids into the UV, and we think it can provide us clues into surface composition. Intimate mixtures of phyllosilicates and amorphous carbon will reduce the overall characteristics of a range of the UV visible primitive asteroid spectra. The darker it gets, if you have an intimate mixture of it, then you're starting to see a decrease in the depth of some of these features. Adding amorphous carbon will have a spectral signature in the UV, but you still can retain the 0.7 micron feature, but it does weaken the UV absorption edge. Amorphous carbon we expect to be a weathering product of native carbonaceous compounds, and that could be brought in either by weathering, by impacts that would cause the amorphous carbon to be formed, or brought in by micrometeoroid, impacts as well. And I think I said most of that anyway. Thank you. So I'm gonna beg off on anything that was completely up and down with the idea that it's still a work in progress. Dan, go ahead.
On your chart with albedo, you had an unfortunate choice of colors. What's the albedo of Vilas?
0.096.
0.0. So that's pretty bright for...
I know.
Okay, just pointing that out.
It's bright for a CGH, but it's a smaller object, obviously. And it's potentially the fresher surface. I won't say it's a pristine surface, but a fresher surface than some of the other ones, which were, just larger diameter, potentially older objects.
Yeah, but a factor of 2.
Sure. Do we know?
It's really hard to make CMs or CIs or C2s that bright just by changing the particle size.
Agreed. But we don't know what the full composition is yet. No. But and the idea with, the other thing is the idea with Vilas being the smallest and potentially the freshest of the bunch that we looked at was that it would not have as many, would not have as much nanophase iron that potentially could darken it, even if it has, and it potentially has carbon as well.
Yeah, but I think the darkening is probably more due to the organics than the nanophase iron.
It has to be at that point. I mean, it's probably. That's what I'm saying, yeah.
What is your method for mixing the carbon with the phyllosilicates?
It's an intimate mixture.
Model?
We're doing intimate mixtures, but we're also starting to do nanophase carbon and seeing how that affects it.
Could you explain a little bit of the methodology just for...
an intimate mixture using happy formulations, and so it's like in the Hapke 1993 book where it's like a salt and pepper mixture. And then the other alternative is also a Hapke formulation, but from his 2001 paper where he takes nanophase, in that example it was nanophase iron, and so instead of a salt and pepper mixture, it's actually little blebs within the grain. And so they can be much smaller size. And it turns out that often that has a stronger optical effect. Did I answer your question?
Yeah, thank you.
Okay.
There. Yeah, they're recording it, that's why. For
Yeah, I've done some of these experiments.
Yes, yes, it is.
I've done some of these experiments of mixing carbon with silicates and looking at the difference in the reflectivity and so on. And they've always bugged me, partly because doesn't it depend very much on the nature of the graphite or the nature of the carbon? If it's sort of lamp black or soot, then it's submicron, it's so fine grained that its major effect is to coat the silicate grains rather than just to lay there like a salt and pepper mix. So
Exactly, and I think that's the modeling of that is in the second type of mixture that I mentioned, the nanophase
but there's
mixture.
no linear relationship between the amount of carbon you add and the albedo, for example. It's non-linear, right?
It is because it has a lot to do with the grain size also.
And the mechanical process.
Mhm.
Yeah, but I think almost by definition, if it's nano grain, then it's that second type of
coating.
mixture that you're talking about, where it's like coating
Yeah.
rather than salt and pepper.
If we've time, I've got a little point for you, Faith.
We're into open discussion period. Go ahead.
Okay. So long as we take as much time away from my discussion. Sorry.
Thanks. No, go ahead.
Okay. You say C chondrites, and you realize that there's a vast difference between a CI and a CO.
I said CM2
You said
carbonaceous
CM,
chondrites.
okay, all right,
CM2
then.
carbonaceous chondrites.
Okay.
There's not one of them that doesn't match the chunk of what we're seeing.
Then I understand. Okay. I have looked at the cathodoluminescence properties because of my interest in luminescence of several CMs, and the fine-grained matrix, the smoky matrix, is awash with submicron grains, which I have always assumed to be forsterite. Now, if that is right, the matrix is awash with olivine, but it's nano size probably, but it's really, really tiny. You said there was no olivine in the matrix.
I went by literature on that. I don't go to the laboratory
Okay.
and work on things. I was taking that from the literature as to what
'Cause that
percentage of
matrix-
this. Yeah.
That matrix is a mess. Yeah, right.
Where we need so little olivine, what we need is the presence of olivine, and we have it. We need a small percentage to be able to see something, and that's all we need. But yes, that's fine. That would be great.
Okay.
Send me a reference.
I
I'd
thought
love
you were
it.
saying it was absent or something.
I was saying, yes, I did say it was absent, and I said it was absent, and I just defined it now by saying that I said it was absent because that's what I got from the literature. I'm not going into the laboratory per se. I go to the telescope as a rule. So, it's, I'm happy to be directed to a correct reference. But our work with the S-complex weathering process, it suggests that we do need a very small amount of olivine we need olivine to start forming into a small amount of nanophase iron to get to where we're going to start seeing the weathering effects in the UV, and we'll see them before we start seeing them in the VNIR.
None of your conclusions were hanging on that comment.
No. My conclusions hang on whether we have any olivine, in which, at the moment, and in fact, basically my conclusions are more work in progress than an actual conclusion in the end for the C complex.
We've seen olivine in cometary dust, right?
Sure. Yeah.
And there you have a range of magnesium rich and iron rich.
And we also have some iron in different forms obviously in the CM2 carbonaceous chondrites that aren't the olivine, and I think they're now showing that while the olivine was the an original driver for the creation of the nanophase iron that people identified in the laboratory and then saw, but they've seen some of that plus other forms of nanophase materials in the return of the very small particles from Hayabusa of Itokawa. So it's not just limited to that, but it is sufficient, and there is sufficient olivine present in the CM2s to suggest that that might be one of the mechanisms that's darkening it. Not maybe the only mechanism. So I would suggest that they were probably parts of the two mechanisms.
There are some spectra for chondrules somewhere. I've seen.
I haven't. I'd be happy to see them.
There are.
Yeah.
Do you have some?
Spectra for condoms?
Yeah.
Oh, yeah.
Okay.
Hard to avoid. I have a comment on an earlier talk.
Sure. Oh, yeah.
So about the
I don't
survival of
have an answer.
water, I got interested in Tagish Lake because there was a fair amount of anecdotal evidence that it was containing ice when it arrived. It's people who would go out into the frozen tundra of Canada and collect it, and then have it sitting around on the table, found that it was soon sitting in a puddle. You know, even stuff that did not have any visible snow attached or anything. And so I did density and porosity on a group of samples that had been curated and stored under frozen conditions the whole time, collected and stored in low temperature. And the porosity was lower than the samples that had been stored in room temperature, and is best modeled by having a component of ice in the meteorite. And so I don't know how that works for survival of ice, because I don't do that kind of modeling, but I think that there are observations that ice does survive in the inner solar system.
Well, there are comets in the inner solar system, right? So
Well, but this is something that started out a few meters in diameter at the top of the atmosphere.
yeah. Well, I mean, I mean, first of all, I'm interested in very long time scales, right?
Yeah.
So, yeah, I mean, you're saying Tagish Lake had ice, or you're saying it had just a lot of hydration?
I just observed, no, it's ice. Structurally round hydroxyls do not melt on tables. So it
Yeah.
was ice.
Yeah, no, I don't, you know, it's, you know, it can be from a polar region. I mean, there are ways of doing that, just the
Right, and
parameter region becomes
It
smaller.
could also be from a very elliptical orbit, right? And
think we know what the orbit of Tagish was.
do we? Okay, so what did it look like?
Oh, well, you know, it was not hugely elliptical.
Okay, so it was in the inner solar system for a while.
Well, I think it was more a standard NEO orbit that it was anchored in the asteroid belt.
Yeah, I mean, I don't.
This is just
don't
an
disagree.
observation.
Yeah.
The main problem is I haven't, I wrote an LPSC abstract on it, and I haven't gotten around to publishing it. I'm
I mean,
lazy.
The thermal conductivity of Tagish Lake material might be very low. I'm not sure anybody has really measured it, which would favor ice.
Well, I think it's pretty standard for that general type of material.
More questions? To anybody who spoke today, this afternoon? Thank you all for coming. I appreciate it. I appreciate your lasting through the last talk.